Hello, you all. Barely Beverly Jr. back for some more physics. We'll talk about some dark matter, and this is something that I'll be talking about in a lab next week. Discussing galaxy curves and how galaxies, when they rotate at a rate that is not consistent with the visible matter that we see in the universe. So what I'll do is we'll look at a few images of the bullet cluster, which I have on the screen now. We'll look at a paper that I read a few years ago when I wrote an article for my astrophysics course at UT on dark matter and dark energy. And we'll actually look at the galaxy, the curves, the velocity curves of an actual galaxy using data from the actual light from a galaxy and see what that looks like. So I'll start off with the bullet cluster, looking at the website that we have on the screen here. This is the first real direct empirical evidence of dark matter. If you look at this image here, this is I remember from my reading, this is not necessarily a direct image of the cluster. And first, what the bullet cluster is. So the bullet cluster is a cluster that's a composite of two different clusters. So a cluster is basically a large grouping of stars. I did some research on that. Awesome. Glad you go. I hope you enjoy, Rabbit. So I did some research on clusters from my undergraduate research. So I'm slightly familiar with them. Can't say I'm in depth familiar with them, but there's different types of clusters, certain clusters with different ages of stars. This particular cluster is a very old cluster. You can imagine that these two large groupings of stars, thousands of stars, they come together. And when they came together, they blended into one cluster that we call a bullet cluster now. And this is the optical view. And, at this point, it looks like it's just two clusters of stars. But assuming one grouping of stars. But if we look here, what we're doing now is looking at the plasma that's at the heart of these two clusters. So if we consider like the sun, stars, they are mostly hydrogen, right? We know that from studying them, looking at the spectra that's coming from them in other ways as well. But for the most part, from the spectra, we know that they're mostly hydrogen, right? And of course, there's a relative good bit of helium compared to other elements. We discovered helium on the sun. A lot of people may not know that we first discovered helium on the sun before we discovered it on Earth, which is where the name comes from. But the thing about this cluster is when you look at this plasma and you look at the stars, again, that's why I mentioned that stars are mostly hydrogen. And plasma is basically hydrogen as well. It is basically superheated gas to where it's so hot that the electrons ionize from the proton, right? So a hydrogen is really just a proton. There's an electron floating around there for good measure. But it's basically a proton. That's what the majority of the mass is. And so plasma is basically a star that's just not in a concentrated space. And the way it works is if we were to take the stars in this cluster, what we see here, the visible hydrogen that's compacted so closely together that gravity heats it up and causes fusion. That's what we call the stars, just hydrogen that's gravitationally close enough together where it causes fusion. And we look at this hydrogen where it's just dispersed enough to where it's not, burning visibly. This plasma is gravitationally stronger. There's more of it than the stars. If you were to take the stars and stir them up so that it's just a cloud of gas, there will be less of a cloud of that gas than the plasma. So the plasma weighs a lot more than the stars. But what we found is that if you look here, you see the distribution of stars. If you look here, you see the distribution of plasma. If you look here, and well, I guess it's hard for me to see. I thought I'd be able to show that, but maybe I'll just show the paper right now. so I can see what that's talking about. So we'll pull up the paper really fast. If you look here, this actually shows the gravitational lensing. So again, on the left, you see the stars. On the right, you see the plasma that we saw. And the green contour lines, those are the lines from the actual gravitational lensing. So what scientists did was they analyzed the image very closely. So look at the light that's coming from behind the cluster, and they were able to analyze and see where the gravitational lensing were. So gravitational lensing is basically the light is actually curved due to the curvature of space because of the large amount of mass that's there. So it's interesting that in we think about the shortest distance between 2 points being a straight line. When we're talking about light, something moving at the speed of light, the shortest distance is actually the shortest amount of time. And the shortest amount of time is not necessarily a straight line, because if you think about it this way, if the light was to come directly to us from behind the cluster, it would run into, let's say, a star or something. So it would either run into something, or gravity will curve it where it doesn't even reach our eyes. It'll reach past us. So the shortest distance between an object behind the cluster and us is the path that's the shortest amount of time given the curvature of space. And that curvature is was being outlined in green here. The curvature due to the large gravitational lensing that's going on. And if you notice, the focus of the lensing is not at the focus of the plasma, and nor is it the focus of the stars. It's at the focus of the dark matter. And again, you have to keep in mind that this is the collision of two clusters of stars. So you may have heard the term dark matter halo. The idea is that when you have a large amount of mass, like a cluster or a galaxy, the dark matter, we understand it to be collisionless. Like it could just pass through anything without any interaction. But it is still mass, so it does have a gravitational attraction. So the idea is that when these two clusters went past each other, the dark matter, since it's collisionless, it just went straight through first, right? And on the left, we're basically seeing a dark matter halo from the cluster that entered from the right. It entered from the right, went past, and it ended up on the left. And the dark matter on the right is from the cluster that came from the left and passed. And then you have the plasma, and then you have the stars that mix up. So the reason why this is relevant is because there's two different major schools when it comes to this discrepancy that we're seeing. And now I need to bring up my images, so that'll be clear. So give me a moment here. I'll bring up my actual curves from the galaxies, and we'll see what that's talking about. So these are actually uh, from the data from a galaxy what NGC 3198. Let me open up one more. All right, so the first thing I'm going to do, I'll show an image of uh, the, what do you call it? Rotation curve of the solar system. Uh, so get boom. All right. So this is some data that I put together. So if you look at this, we have the speed, the orbital speed of the different planets in the solar system relative to each other. And I'll go ahead and maximize this. Don't mind that I won't be visible for it momentarily. Or I could just actually just put it behind the camera. So no big deal. All right, there we go. So if you look at this, it actually goes from the planets inward to outward. So on the left, where you see 0.439, that's the distance of Mercury from the sun. So what I did was I took stellarium. I'm actually preparing I'll be the teaching assistant for a lab next semester, an astronomy lab. And a large part of the lab will be using stellarium. And so for one of the assignments in the lab, I had already gotten the distances from the sun of all the planets at a certain date. So this is for January 20th of next year. Mars is about 0.49 AU from the sun. So what I did was I took the distance from the uh, uh, sun. I used Kepler's laws to get uh, uh, the period of orbit, which does match the gravitational period and other data. And then I use that to get the velocity. So if you have the orbital period, you have the distance of the orbit based upon the radius. The velocity of Mercury around the sun is about 44 kilometers per second. And if you go outward to Venus, which is about 0.7 AU from the sun, its velocity is about 34 kilometers per second, and so on and so forth. And as you can see, the velocity very much decreases as we go outward, which makes sense. You're farther from the center of gravity. In the solar system, most of the mass of the solar system is focused in the center of the solar system, in the sun. So you're farther away, so you're going to go slower and slower around the sun the farther away you go. This is basically the velocity curve of the planets around the solar system. Now let's look at the velocity curve of an actual galaxy and see what the difference is. But we look at this is from data from an actual galaxy, galaxy NGC 3198. I don't know where to get the names from. I didn't look at the naming convention very much. But the students in my lab will be soon making a plot like this as well. Now you look at this, at the bottom, the x-axis, you can see that this is distance from the center of the galaxy in kiloparsecs. And the vertical axis is the velocity going around. So this is the exact same plot that I did with the planets, but now we're looking at the stars, the gases, and so forth that are rotating around this galaxy versus the planets rotating around the sun. And as we can see, it starts off from the center of the galaxy, not going very fast. It starts to speed up as we go from the center of the galaxy, and then it levels out. So from about a quarter of the way from the galaxy to the edge, you can see everything is going at almost the same velocity, about 150 kilometers per second, which is quite amazing. All right, so let's compare this again to the solar system so we can really see the differences in what's going on here. So this is very important. Looking at the solar system, the farther we get from the center of mass, from the sun, the slower the orbit gets. And we know this from experience, right? If you have like a ball or something on the string, and it is interesting, right, Riker? You have like a ball on a string and you're rolling it around. When the string is it's short, it goes faster. If you make the string longer and longer, you know that it generally takes, goes around slower. You have to twirl it a lot harder to make it go faster with the string being longer. But we see that that's not happening with the galaxy. And we see that every single galaxy we look at, this is the way it is. The rotation curve is nowhere near what it should be, which means something has to be going on. Something has to be going on with the mass that allows this the mass to be more distributed than what we will see. And if you could imagine, if you're looking at a galaxy, visually it looks similar to what we see with a solar system, right? There's a core to the galaxy. Usually it's very bright. There's a whole lot of stars clutching around the center. And as you move outward from the center of mass, it starts to peter out. And of course, the Earth, we're towards the end of an arm of a galaxy. So we see that pretty clearly. We look up at the sky. You know, we get a telescope. You can see a lot of stars, but compared to the center of the galaxy, it's pretty sparse out here. So visually, we see what we would expect to see. The farther away you get from the galaxy, the less populous it is with stars and things, the less dense it is, as we would expect, because the center of mass is more dense. But the light curve, the velocity curve, I mean to say, is totally not reflecting that. So what we did next was I actually did a calculation where I did a calculation of what the mass would have to be to simulate this. So what this graph is showing is I looked at the velocity curve of the galaxy, and I compared that to the angular acceleration that would be needed given a certain amount of mass to keep that rotation going, to keep that rotation consistent. And doing that calculations, plotting that data, this is what I got, which means that if we're looking at the mass enclosed, so for instance, if you could imagine, if you think about it this way, gravity, the way it works is if you have a spherically symmetric uh, 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 piece of mass, and Riker says the difference is fascinating and it's incredible work, Daryl. You're amazing. Thanks. I'm glad you appreciate it. And so this is even though it's talking about just the solar system and the galaxy, dark matter we now know makes up the majority of the universe, right? So this findings like this actually give us a great insight into how the universe is structured. And I imagine one day we will have an understanding of what dark matter actually is. Right now we can't say exactly what it is. We just we can see that it has a gravitational effect. We observationally it seems to be collisionless. Like we don't see things bumping into it. So it behaves as if it's not there, except for that it has the gravitational effect, which we can see here, right? The way gravity works is if you have a bunch of matter, that's distributed, gravity will only act upon the mass that's outside of it, right? So in other words, if you have a sphere of mass evenly distributed, the matter outside of where you are, like if we was to dig into the center of the earth, let's say, and you was to go to the center of the earth, if you go into the center of the earth, the very center, you will be weightless. It will be like you're floating in outer space. Like if we was to hollow out the center of the earth, and in the very center, like let's say you had a mile wide orb in the center of the earth, we deposited you in that center, you would just be floating, because all the mass outside of you cannot act upon you, because the gravitational attraction for the mass here is being balanced by the mass over there. So only the mass that's within or inside the radius of your position within that mass affects you gravitationally, right? Like right now we're on the planet Earth. On the surface, what's pulling on us is the entire mass of the Earth. So whatever is within your radius pulls upon you as if it is a point mass, which is to say, the gravitational effect that we're experiencing now, we would experience the same gravitational effect if we were to take all the mass of the Earth and crush it into a point. If you took all the mass of the Earth and crush it into a point at the center of where the center of the Earth is now, and I drop this mug, it will fall the same exact way as right now where the mass is distributed. So we understand that to be the case. So when we look at this galaxy, we could apply that principle and say at this radius. So looking at the graph at 3 kiloparsecs from the center of the galaxy, how much mass would need to be within that radius to cause that velocity curve? At 10 kiloparsecs on the x-axis, how much mass on the y-axis would need to be there to cause that light curve, and again that velocity curve? And again, if the velocity curve is the same velocity curve, we're looking at how much mass is necessary to cause the velocity curve that we saw a moment ago, right? So when I calculated this is what it looks like. We can see that the mass curve is linear, which means that the mass is evenly distributed throughout the galaxy. And in a very linear way, as you move forward from the center of mass of the galaxy, the amount of mass within that radius linearly increases. And we know it can't be the visible matter because we know the visible matter, we can see it. It peters out as you get away from the center of mass. And that is where the dark matter mass has to be behaving to cause that velocity curve, right? So all of this stuff I find very interesting. And we'll be covering it in my lab coming up. And do I still have the paper up? Yeah. So I'll close this and leave the paper up. So yeah, so this article is by Flo. I forget when it was actually published. Let's take a look and see when it was originally published. In 2004. So years ago, I had read this paper, and it was a major component of my article about dark matter. But I thought, I think this finding is amazing. How so if you think about all the things that played into this discovery, like the understanding of relativity, understanding that space curves due to matter, like even around our bodies right now. And Riker says, so there's more mass at the outer edge of the galaxy, which is dark matter. That is correct. If you look at the galaxy or any galaxy or even its cluster, there's more mass there than we can see. And it has to be, we know it has to be because we can see, to show that image again, we can see the velocity curve that we know has to be there because mass is causing that thing to spin that fast. So we know there has to be more mass there than we can see, or else the curve would be looking like this. If there was not more mass than we can see, the velocity curve would be looking like that. This is the curve because if we look at the solar system, there is dark matter here, but the amount of dark matter between us and the sun is nowhere near the amount of dark matter that's within an entire galaxy, right? So within the area of a solar system, the mass that's having the biggest effect on the velocity of the planets is the sun, right? Therefore, the farther away you are from that gravitational influence, you have to go slower to stay attached, right? If Neptune was going as fast as Mercury, being that it's farther away from the sun and gravity, it falls off as 1/r². The formula for gravity is F equals G, the gravitational constant, the two masses mm divided by r². So the farther away you go, the smaller the gravitational pull. So if Neptune was going as fast as Mercury, it would just fly away because there's not enough gravity to hold it. There's not enough gravity to hold it, so therefore it slows down, right? And that's why the farther away you go from the center of mass, from the sun, those rotation curves get slower, right? Because there's not enough gravity to keep it in place. But that means, to your question, Riker, the only way this velocity curve can be what it is for a galaxy, and we know that's what it is because we can see the stuff going around. We can look at it. We can now galaxies, they spin, like if you look at this galaxy curve, we can see that the stuff on the outside is spinning at about 150 kilometers per second, right? So we can't stare at a galaxy long enough to determine that speed. But what we can do, we can look at a galaxy and look at the light that's coming from the galaxy, and that galaxy, how it's oriented towards us, the part that's spinning away from us is going to be redshifted. Like the light that's hitting us is going to be a lower frequency because it's moving away from us. And the light from the part of the galaxy that's spinning towards us, it'll be blue shifted. The frequency will look like it's going faster because it's being moved towards us, just like how I'm sure we've all been, standing on the side of the road at crossing a street, or in our car and an ambulance goes by, and we know when an ambulance is coming towards us, the sound is higher, and then when it passes us and it gets lower, as it's moving away. But the same thing happens with light. So we look at that light, and we can, we know, for instance, in a laboratory, the frequency that helium gives off or hydrogen gives off. So we can look at the difference, and we can see how fast that galaxy is spinning. We know it has to be spinning this fast because frequency of helium has boosted up this much on this side, and it slowed down this much on that side. So it went this far from the rest frequency of helium or hydrogen, whatever we're looking at. And normally we look at the 21 centimeter line of hydrogen. So we know how fast it has to be spinning. That's how we get the velocity. So we know, since this mass out here is going that fast, we know how much mass has to be there to get it going that fast. And thus we know that it can't be stars, because we can look at the stars and see how much stars are there, and we know dark matter has to be there. And Riker says it's fascinating that it becomes linear from a certain distance going all the way out. Yes. And that'd be because, if you think about it this way, if you are at the North Pole, right? If you're all standing on the North Pole, right? As far as the rotation of the Earth, you're spinning in place. So your rotation curve is not going to be that fast, right? But if you're standing on the equator and someone is in space looking at you go by, it'll look like you're going by at 1,000, at with 1/24th of the rotation of the velocity of the circumference of the Earth, like 1,000 miles an hour. I believe it's like 24,000 miles across. So that's all it is. If you're at the center of the galaxy, even if your rotation curve is not going to stand out so much, but as you get farther and farther away, that radius increases, and thus that moving around actually sticks out, and thus we get to see the curve better, right? So that's what that's about, right? I imagine that the black hole in the center is probably spinning as fast as everything else, but it's just spinning in place. So we're not going to really be able to capture that so well. So that's all that is. Just like on the Earth, you notice all of this stuff is consistent. You stand on the North Pole, you're just spinning in place. You stand on the equator, you're going by at 1,000 miles an hour, right? You're in the center of the galaxy, you're just spinning in place. But if you're at the edge of the galaxy, well, now you're going around the whole galaxy, and you're going pretty fast, right? Right. So that's what that is, and same thing with the solar system, except the solar system, again, we don't have enough mass to keep that velocity consistent. So everything has to slow down, or else we're going to spin away. And thus you have Neptune going at Neptune is the farthest planet out. It's going 5.4 kilometers per second, versus Mercury is going 45 kilometers per second. Right. So it's all pretty consistent, no matter what you're looking at. Whether you're looking at a solar system, whether you're looking at the orbit of the revolution of the planet, or you're looking at stars and things going around a galaxy. So it's pretty cool. Now, I would mention, by the way, that there is a camp in physics, astronomy, that does favor the idea of a modified Newtonian law. So what they do is they posit that if you have enough mass, Newton's laws break down. And the equation I gave you earlier, F equals G mm over R squared, that goes down, breaks down, and we have to add some kind of scaling factor up in there. So what they do is they take Newton's laws, they put a scaling factor, and what they would do is they would look at this galaxy curve and say, we're not going to scale up the mass and say, okay, the enclosed mass must be increasing. We're going to say, you know what, there is a consistent amount of mass, just like there's with the solar system, right? They say, well, the mass goes down in the galaxy, just like the mass goes down in the solar system, but if I alter the laws a little bit and put the scaling factor, this will account for that. So what they're saying is just the laws break down, and they add the scaling factor to artificially boost the gravity, and they make it work that way. I don't agree with that because we have the bullet cluster now, and we to me that's pretty convincing, and that's why the title of this paper, if you look at the title, they were not bashful at all. A direct empirical proof of the evidence of dark matter. Now, I mean, they pretty much said, without saying it, modified Newtonian laws is wrong. Right now, the fact is there is still room for both. I mean, it's possible there could still be some kind of small, adjustment. Like we know that when you have speeds that's very fast, we have to alter the laws. That's where special relativity comes in. We know as we start to move at speeds close to the speed of light, and those who watched the stream last week, you saw me do direct calculations on that. We know that the size of things is altered, and we know that the time around things is altered. So when you start going at relativistic speeds, time and space are not consistent, right? They start to bend, they start to alter, right? So it's still possible that with large amounts of mass, things alter. It's possible, but it's definitely not the whole of it. I mean, I think this paper and this finding and this bullet cluster with its gravitational lensing is pretty conclusive that there is some kind of mass there that we don't see, because again, the reason why this is relevant is because even if there's some modified Newtonian law, those Lindsay curves are not around the visible matter at all. So they're not around the stars, and they're not around the plasma. So it's pretty convincing to me. So yeah, it's pretty cool stuff. So I found it interesting. Always thought it was an interesting thing to talk about. That's why I wrote about dark matter, and I wrote about dark energy, which is maybe relevant to note that even though the terms of the two things, even though you call one dark matter, you call one dark energy, they're not relating to the same thing at all. It's not like there's some um, type of, I mean, there may be, but the term doesn't mean that there's like some kind of energy out there that's dark that we have to somehow, I don't know. It is basically a weird term that's referring to the fact that there's something out there that's causing the expansion of the universe to accelerate. And they sort of call it dark because we don't exactly know what it is. Now, one of the recent findings with DESI is that the expansion is not consistent. So currently in some areas of the galaxy, if you look at a larger scope of the galaxy, the expansion is decreasing, um, is not a constant increase as we thought it was. So that's yeah, some big things are changing with the dark energy world. But I just want to point out that dark matter and dark energy don't really refer to different aspects of the same thing. It's just totally different concepts that have slightly similar names. So that's pretty much all I had. A pretty short, well, I guess about 40 minutes. I mean, not going a full hour. You have any last questions, Riker, before I close up? Any last questions, any last comments, any last concerns? Thanks everybody who watched. Hope you like and subscribe if you haven't already. And going into some concepts and particulars today. I'll show the image on the screen as well while we close out of the galaxy curve. I guess I'll show the mass curve. The dark energy mass that must be there is causing that velocity to stay high. Awesome. Thank you all for watching. And I'll be back next week. I'll probably do a more in-depth calculation one next week. But I think last week I must have been like 6 hours or 7 hours doing some calculations. So I figured it'd be nice to do a little more concept-y and observation-y type stream. And if you have anything that y'all interested in, let me know. I could delve into that as well. But I'll probably do some more relativity next week since I plan on doing. We're able to pick between certain problems. So I know I'm gonna do a relativity problem on my final exam in my classical. A lot of people may not know that relativity, special relativity, is actually a part of classical mechanics because the speeds, even though it's relativistic speeds, even though you're going at near the speed of light, you're still going at a constant speed, which means you're still in an inertial reference frame. So special relativity actually falls under the umbrella of classical mechanics. So you actually do special relativity in mechanics, which I'm doing in my graduate classical class. And Riker says, do you mean mass getting so large like a black hole that the equations break down? Yeah. Either the mass is so big, a single mass, or because you're dealing with a lot of mass in total, right? So you could either be dealing with a dark black hole or a neutron star, or like the bullet cluster there, right? Even though you may not have a lot of black holes in that cluster, you still have a whole lot of mass. So the idea is that whether you're dealing with something that's very massive like a black hole, or you back up and you look at a galaxy, or you look at a cluster of galaxies, because you're dealing with so much mass together, the laws break down, right? So that's the idea behind that, behind the modified Newtonian laws. Whether it's one concentrated piece of mass, or if you're going to look at that sector of the universe, right? Because if you back up enough and look at the universe as a whole, it becomes these big webs of matter, these big webs. They call it the cosmic web. So that'd be another, if you look at this area of the web, they will say that because you're looking at such a big area of mass, the laws will break down. So, but having liberty to look at minds in detail, I've seen a few, sometimes speakers come, they call it colloquium, or speakers will come and visit the university and give a talk. And when I was at UT, one of the people who promote that came. Either it was a visiting speaker, or it could have been one of the like postdocs or somebody at there. But somebody gave a talk on it. And it was talking about modified Newtonian gravity. So there are people who support it, but I haven't really looked into it in detail, because I actually, the bullet cluster, when I saw that, to me that's pretty conclusive. So the fact that the center of those gravity curves, the gravitational lensing, is neither at the plasma nor at the stars, that's conclusive enough to me. So even if you have some modified Newtonian gravity, this finding here with the bullet cluster lets us know that the effect will be much smaller than the effect that dark matter is having. The classical correlation would be, I mentioned how when you get to relativistic speeds, you have to use relativity because time and space alter, right? But you can, if you wanted to, calculate, basic stuff with relativity. Like you can calculate if you wanted. I've never done this before, but the equations are there. You can calculate, dropping a mass from a cliff, right? Instead of using kinematics to do relativity, if you want, you would end up with a more accurate answer. But instead of it taking 10 seconds to hit the ground, you might calculate 10.000000005 seconds. But what's the point of doing that, right? 10 seconds is good enough, right? If you're going to build a bridge, you don't need those 0.0000005 seconds. You just 10 seconds and you build a bridge, or right, whatever you're going to do. So it's not necessary. So to me, just going off what I think about it, I would say any adjustment would be similar to that. Okay, so you get a large amount of mass, you're going to have to, whether it's a black hole like you were saying, or whether it's, now I'm looking at a cluster and I'm going to have to calculate something around, how fast I'm going to orbit this cluster of mass, right? Maybe you have to alter the equations a bit so you get this small decimal or something, but you should be able to just get the right answer by acknowledging that there's dark matter there and take into account that dark matter right? And then you just get a rotation curve like we get with the galaxy here. I'm just taking into account dark matter and whatever altering you might need, it'll be very small, right? That's my take on it. But again, I never looked at the modified Newtonian gravity in depth because uh, I don't think it's correct. But again, there's still room for people to find some way it actually fits, even though dark matter clearly is a large impact. Thanks for the question, Riker. It's awesome. I'll be back next week, same time. If I don't come before then, I'll probably be here throughout the week as well because we have some exams coming up. So you all know I like to work on practice and problems and stuff like that. So awesome. Thanks to everybody for showing up. Thanks for your questions, Riker. Thanks for your comments. Always good seeing you. And I'll see everybody next time.